Thank you, and good morning, everyone. So just going to start right off the bat here. Interactive data visualization on the web is a really thriving area. You've probably heard some things about it. It's a super exciting, and I have to say, a really collaborative sub-community within the broader web dev community. So if you're interested in it, get involved, because the community is really great. But that's not to say that working in this area is rainbows and sparkles 100% of the time. When you're building a visualization on top of a large real-world data set at scale, there can be a lot of challenges. And so what I'm going to talk to you today about is sort of all the things that I wish somebody had told me before I embarked on the project of writing a large data visualization library. And so this is basically the tool set that I've gathered for myself over the last couple of years of work, and I hope it'll be useful to you. So we're going to talk about the most widely used tool set in interactive data viz on the web, and that's the combination of the JavaScript library D3, which stands for Data-Driven Documents, and the SVG image format. So you use D3 to build things in SVG commonly. If you're not familiar with SVG, it's a vector image format that's XML-based. So that means that all the components of the visualization are XML elements that sit in the DOM just like HTML elements. In fact, most SVG properties can be styled through CSS style sheets, although not all of them can be. And just to give you a little overview of where we're going, so I'm going to start with just a little bit of an example of one of the SVG basics that's a best practice, in my opinion. And then that's going to lead us into a discussion of performance problems, especially with SVG. And we're going to talk about how to profile those. And then I'm going to wrap up with just a few tips for how to solve performance problems. And that'll be a couple of general strategies and a couple of other JavaScript libraries that are good tools for working with large data sets in particular. So I say that D3 plus SVG is the most common tool set. And why is that? Well, it's because what D3 actually does is bind data. So we've got these little miniature JSON objects that I created, to elements in the DOM. So those are commonly SVG elements, like this circle element. So you can use D3 with something like Canvas, but in my opinion, that should be sort of the option of last resort, because you're actually losing a lot of this power of D3 if you use Canvas, because Canvas is a raster image format. And so the only element that you actually end up with in the DOM in Canvas is the Canvas element itself. And so you're losing this whole power of binding data to DOM elements, and basically all the functionality in D3 is around manipulating those bindings in various ways. So once you've learned those interfaces in D3, and it's basically around 3 selections, you'll hear people talking about the enter, update, and exit selections and the patterns of programming around those selections. Once you've sort of learned that core functionality, there's actually not that much else to learn with D3. D3 provides a lot of useful functionality for manipulating and representing data according to some very common data visualization patterns. But in a lot of ways, it's actually a really elegant, concise project. And there just isn't a whole lot more there. The real challenge, in my experience, is that if you really want to become proficient at data visualization, you have to become proficient at SVG. You have to really understand SVG. And so the thing that I want to talk a little bit about that's really important with SVG is using group elements. So this is an element in SVG that's pretty much parallel to a div in HTML, except for the difference that you can get away with not using it. I think it would be pretty strange if you had a lot of HTML that had 0 divs. But there's basically 3 good reasons to use this group element, and that's organization, just organizing your code, providing hooks for interaction, and then also it has performance implications if you don't use them. So this is probably pretty tiny, but all you really need to see here is that what we've got is an SVG with a totally flat structure. We're just dumping stuff into this SVG element. And this is actually the SVG that I hand-coded for that diagram I showed you about binding data to DOM elements. So this is just everything in that diagram all at one level. And so here, it's not too hard to understand, but you can see that in a much bigger project, much bigger than that little diagram, debugging something like this in your console is going to, inspecting it to examine how things are layered would be a challenge. One thing with SVG is that order matters a lot, so you do have to inspect the console a lot. There's no z-index in SVG, so you have to put things into the SVG element in the order that you want them layered. So here's an example where we're actually using groups to organize things. And in fact, each row of that diagram binding one datum to a DOM element is a group here. And what's nice about this is that the groups actually give us hooks for interactions pretty easily in lots of different ways. Here I actually did a native SVG animation, but you could also apply a class to each group. Wow. And do it with CSS animations. You could do it in the JavaScript. SVG is another one of those areas where, like a lot of things, there are probably 100 ways to accomplish a single task. And now here's the third reason to use groups. There's actually performance implications if you don't. This is a little bit of a silly example. So all I'm doing is I plotted 5,000 random data points in a scatter plot. And then I'm shifting them all by a certain number of pixels. And in this GIF of the example where I did this, if you shift after you've plotted all those circles inside a group element and you're shifting them by applying a transform to the group, it's basically negligible performance. It happens in 0 milliseconds, 1 millisecond. If you do it the dumb way by just plotting all the circles, selecting them all, applying a transform to all of them, that actually takes a little bit of time. Now, it's still not noticeable to the user because it's like 12 milliseconds. But the point here is that the more complex you're getting with all of these things, all that stuff is going to add up. And so that is leading me straight into this discussion of profiling performance and data visualization. So just like any experience of a website or a web application, when you're doing something with interactive data viz, obviously you want it to be snappy and crisp and smooth. You want your users to have a good experience and not have any noticeable lag or desynchronization or stuttering. But sometimes that's just not what happens, especially in my experience, like in the first iteration of a new project. So I'm going to talk about how, in the past, I've figured out what the problem is that's causing some performance problems from the point of the user and how to solve them. So these are kind of from the most obvious to maybe the least obvious. There are 3 things that I do a lot to profile the performance of a data visualization. And that's just putting timers in my code, using the frame rate meter in Chrome's developer tools, and recording a more detailed timeline profile. Also, I use Chrome's developer tools for that. I think some of the other browsers have similar tools, but I do believe the frame rate meter is actually unique to Chrome. So timers are a pretty obvious beginner technique for profiling performance, but that's not to say that it's not useful to talk about them a little bit, I think. I almost always now wrap a timer around the main render method in any visualization I'm working on, because the render method, which is where you're actually manipulating the DOM in response to the data or updating it, it tends to be the most expensive part, and especially if you are starting by working with maybe a prototype data set, a data set that's not actually the real data set, and then you're going to scale it later, you should have a timer around that render method so that you can keep an eye on it as you go to scale. I've been bitten by that before. I also prefer to use the console.time and timeEnd methods. I don't know if everyone knows about these. They're really useful. You don't have to do the calculation of the elapsed time. Not every browser supports them, but Chrome certainly does, and I'm pretty sure Firefox and Safari do too. But the only other thing to say about timers is that obviously you have to know where to put them. If you don't actually know where your performance problem is, then this isn't going to help you. So one of the places just to get an idea of where you might have performance problems is spying on the frame rate of your visualization or of any interactive web application. This is something that also I think applies a little more broadly. So I'm not going to walk you through the steps here of like how to turn on the frame rate meter, but this might be useful, which is why I gift it for you. But an important thing to note about how you do this is you actually have to have the developer tools open for the frame rate meter to stay there. It'll be in the upper right of the viewport. So I often pop the developer tools out and minimize them if I don't actually need to inspect stuff, and then leave it open. And I leave it open a lot just when I'm developing. It's a good thing to keep an eye on. And it can actually be fun to surf the web with the frame rate meter on and see what other people's websites are doing. So this is an example of having the frame rate meter open to profile a certain interaction. So in this case, it's, again, a little bit silly. I put this button in there to invert the Y scale of this scatter plot. And there's actually a little gradually increasing delay on the interaction, or on the which data point moves to make the animation. What I want to point out here is that this is the frames per second that you're seeing in this interaction, and this 30 to 60 here is the range, and so that's showing us that throughout this, none of these dips on the timeline are going below 30 frames per second. And then here's an example of the same interaction, but this time I plotted 5,000 data points in the scatter plot. And that has a considerable negative impact on the performance. As you can see, the frame rate has dropped into the 20s. The range we have now is 5 to 60 instead of 30 to 60. And another thing that I can just point out here is that performance in data visualization is often a really simple numbers game. If you're plotting more things, if you have more elements in the DOM, things are going to be slower. So this is straight from Chrome's developer tools, and it's just showing you what's in that frame meter display. So there's the current frame rate, the range, as I said before, that's the min to the max. There is this cute little histogram that's a little hard to read, but can be useful, especially if you leave the frame rate meter open for a long time. You can kind of see over time where, where it's weighted, and then the timeline as you're doing things. So this is my biggest caveat about using Chrome's frame rate meter. It is that main reported number is a running average. And so it's not quite the right tool for really precise identification of problems. Basically, it's good for ballparking and getting a general idea of how, if you leave it open for a long time while you're working, you get a really good idea of how well your website is performing sort of between refreshes. Or you can set up some little tests and get a sort of general idea of whether this interaction is doing well or not, but it's not going to really pinpoint anything for you. It's just not good for that kind of surgical precision, as you might call it. And so when I first started using the frame rate meter, it was really good for me. It gave me this quantitative picture into performance that you already have sort of a intuitive grasp of, but it can be really helpful for really finding problems. But I didn't really know what the numbers meant at first. So here's my little guide for you on what the numbers really kind of mean. And basically, I would say anything above 40 is just pretty good. Your users probably aren't noticing any lag or stuttering because any of those things are just rare or pretty subtle. 30 to 40 is where a really discerning user might be noticing something like a little bit of lag, or they'd say oh, this could be snappier or smoother. And then under 30, that's where I think people are really going to start to notice. You'll obviously, no one's going to say to you, the frame rate of this is slow, unless they have a background in animation or something. But they might notice, they'll describe it as sluggish or laggy, not smooth. All right, so now moving on to profiling with the timeline tool. So this is the one where timers and the frame rate tool are not really good for finding the code that's responsible for your performance problem. So that's where you really need this tool, the timeline. So in this example scatterplot, silly example that we've been looking at, this is the function that I've been using to generate data. And I'm just going to show you another version of it for comparison. So here's the original version. Now, this one, the generate data slow function, is this is going to be our white whale. I put this example in here so that we can find a bottleneck using the timeline tool. And this is actually inspired by some real mistakes that I've made. One of the difficulties with dealing with a lot of time series data is that different parts of your code might expect dates and times to be in different formats, like strings, JavaScript date objects, epoch integers. And especially if your code base is complex, these different modules have these different expectations, you end up parsing and reparsing date times in different ways many times. And datetime parsing is usually pretty expensive just because it's pretty complex. And so that can really end up causing problems. So this particular example is obviously really silly because this is not a complex code base at all. And the problem here, just to really point it out, is that I'm creating a new date and then immediately formatting it out to an ISO formatted string. And then when I'm actually pushing the data into the array, I'm parsing it again with date.parse, which produces an epoch integer. And then I'm parsing it again with moment, which is a JavaScript utility library for dealing with date times, and then getting the day of the week out. And this is actually even a really slow way to get the day of the week out by formatting it into a day of the week with moment. So again, here's just a little demonstration of the workflow that I use to set up a timeline profile in Chrome's developer tools. Not going to walk you through it step by step, but I'll point out that, so I've set it up so that you get it all in a frames view, which is in these vertical bars. And there's color coding on those vertical bars. There's blue for loading, purple for rendering, green for painting, and then yellow for JavaScript. So basically, when I do this, I always zoom in on the tall yellow bars to find potential JavaScript bottlenecks. And when you're looking for bottlenecks in this timeline, in the flame chart view, which is the view that I prefer, and we'll look at one in detail here in a minute, you want to remember that width represents time, and that's the dimension that you're really interested in. The vertical nature of this flame chart view represents your call stack, but it doesn't really matter at all how long that is. If you have a huge call stack, as long as it's not taking up very much space in terms of width. So really, you don't want to get too concerned with that. Basically, I look for things that don't make sense in terms of width. And another thing to note here, and this is actually something that took me quite a while to track down when I was first doing this. And I've linked the Stack Overflow answer here. These slides are online. Is that sometimes you'll see in these horizontal blocks that a function call is split up into more than one block. And that confused me at first because it sort of looked like some function that I thought was only getting called once was getting called more than once. But it's actually not significant when that splitting up happens. It has to do with how Chrome or another tool is like statistically sampling your call stack to produce these charts. And sometimes things get split up and it's not significant. So here's one example of one of these timeline profiles. And this is for the original data generation function that's not slow. And this is probably a little small, sorry for that. But this part here, I'll try to do both sides, is the amount of time that it's taking to generate the data, and it's about less than half of the blue box, which is for drawing the data. Now that makes sense. That's not strange because, as I said before, usually the part where you're actually rendering and manipulating the DOM is the most expensive part of any data visualization rendering. So that makes sense. That's fine. Now here's what happens with the white whale that I put in for us to find, the generate data slow function. Now the data generation, again, the black box is taking like 3 to 4 times longer than the drawing. So what you would want to do here is look into the call stack, into these functions that are being called below inside that generate data slow. And I can tell you that what you see if you're in the Chrome Developer Tools, and you can hover over things there, and it'll tell you the name of the function, or it'll at least tell you what module it's from. These are all calls within Moment.js because of some of the silly ways that I did the times and asked it to reparse this date time. All right, so that's the 3 tools for profiling performance. And now I'll briefly just talk about a couple of general strategies and tools for getting over some of these performance problems, other than being intelligent about how you deal with your time series data. If I was asked to distill just everything that I've learned about making performant interactive data visualizations into a couple of statements, these would be it. The first one is that if you ever have a choice between implementing your own version of something in JavaScript and going with a browser native version, use the browser native version. And I'll have a specific example for you here in a second. And then the second thing is to try to change the DOM as little as possible, just because that's the most expensive part of this whole process. So I've spent a lot of time over the past couple of years working on horizontally scrolling timeline visualizations of data. And there's 2 basic strategies for implementing this kind of thing. One is to render a really wide SVG that you're only seeing part of at any given time. And then you're using the browser's native scrolling capabilities for navigation. Or you can render the SVG exactly the size of the portion of the timeline that you want to be in view at any given time, and then attach mouse events and touch events, and change what you're actually rendering within that little SVG as the user is interacting with the display. And so that's your navigation. So at first, I really thought that the second strategy made more sense because I thought the rendering a really wide SVG strategy was kind of strange and counterintuitive. But after having performance problems with that original implementation, I did a lot of experimentation, and I've really changed my tune on that. And I think that it really makes sense because browsers have obviously put in a lot of work and optimization into something like image scrolling performance. So it's really not that much of a surprise that using the browser's native scrolling abilities there is more performant. And here's a little bit of evidence for that. Here's the JavaScript version. The frame rate was in the 30s. And this is a toy example that's not even remotely as complex as what I was actually working on for my company. And then here's a browser native version, which has a frame rate that's way up in the 50s. And the code for these little toy examples that was just in these GIFs is on blocks.org. If you don't know about this, Blocks is a website that is also maintained by Mike Bostock, the primary owner, author of D3. And it's built on top of GitHub Gist. So you just put your GitHub username into the URL, and it renders things. So if you have an index.html, it'll render it. So it's a great place. And it's basically where the D3 community puts all of their code examples instead of something like CodePen or something like that. So it's a great place to look for D3. And I'll put the URLs later for my particular Blocks page if you're interested in seeing these examples. So lastly, don't my final sort of tip is to not touch the DOM, or to try not to touch the DOM as much as you can. And this is, again, something that's not particularly innovative. Obviously, like Facebook's React is an entire front-end UI framework that's kind of built around minimizing DOM manipulation. But just because it's common knowledge basically doesn't mean it's always easy to remember. So I just try to think about it a lot now while I'm working, like asking myself constantly, how much am I changing the DOM? And can I avoid it if I am? So for example, if my data set is really large, like this huge scatter plot, probably there might be even a better strategy for visualizing it by aggregating it or introducing some smoothing. And that will probably result in fewer elements being rendered and modified. And then another thing is that if you're coding an interaction that involves constantly removing nodes from the DOM and adding new ones, which is basically exactly what you're doing when you're doing a timeline that scrolls, is there a way that you can recycle the nodes that you're about to remove so that you can reuse them? And basically that means just changing the data that's bound to them so that you're not removing them and then adding new ones. You're just recycling the ones that you already have. And then my last tip is for dealing with large data sets. There's a couple of great helper libraries for this, CrossFilter and PourOver. These are both open source tools. CrossFilter is probably your first choice for a filtering helper with D3. It's written by some of the original authors of D3. And it provides just a real wealth of functionality for numerical querying and MapReduce. And then PourOver is a little bit different, and the original use case for it was client-side faceted search. So basically, if that is your exact use case, then it might be the tool to look for first. It's basically sort of tag filters in many combinations kind of use case. So that would be worth checking out. So just to give you a very brief overview, my tips for powerful data visualization are to learn SVG as much as you can, profile as you work, and strategize. Let the browser do as much work as possible, touch the DOM as little as possible, and use the helper libraries if your data is really big. Thanks.